Okay, so let's look at this third problem had slightly more difficulty, so let's do that third one. 3.4.167. Okay, so they want, so there's several parts here. Let's work through it. So this is a professional hockey player, 20 seasons, number of games in which he played. So looking at how many games played by a hockey player over 20 seasons. And so they first want the quartile. This is part of the 5-number summary. So we'll just go ahead and go to StatCrunch. Mine is up and running now. Maybe. There's quite a bit. I don't know. I don't know. But probably for this course, um, Excel will do everything you need. But this is really convenient because you don't have to type in all the data. So you just click this button right here. The data's already in your column. So I don't know. So you're welcome to use Excel, but I think this is super convenient. Okay, so then we're going to go to Stat, Summary Stats, Columns, Variable 1, and we want to make sure we have everything we want for the 5-number summary. So the median, first quartile, third quartile. Was there something else? I think, yeah, IQR, is that in there or not? Yeah, it's there. Oops, I just deleted them all. So I'll just go ahead and do all of these. We don't need any of that. All the way up to IQR. All right, and then we'll compute. Gotta love StatCrunch. Okay, so it's just telling us everything there about that we asked for. So the first quartile is? Did you guys have the exact same set of data? Sometimes you have the different numbers for different, yeah. So, but for me, it was 65.5. Second quartile is the same as? The median, right? The median and the Q2 is the same exact thing. Q3. Okay, and we'll see how we're doing so far. Excellent. And we're going to press continue to see more. All right, interpret the quartiles. Choose the correct answer. So let me zoom in on this. Okay, the quartile suggests that 25% of the seasons have less than 65.5 games, 25% are between, 25% blah, 25% greater than 78. So do we agree with that? Were those the right numbers for the quartiles? Yes. And it's saying that there's exactly 25% of the data in between the quartiles. So we think A is true? Yes. Let's mark it and let's read the others. 33%, 33%, 33%. No. Quartiles, right? Quarter, 25%, right? So the name is very indicative. All seasons fall between 65.5 and 78. How many of the seasons fall between 65.5 and 78? If we were to change C, how would we change it to make it right? How many seasons fall between 65.5 and 78? That was Q1 and Q3, right? She wants 50%. Yeah, 50%, right? It's because it's 2 quartiles. So you're basically from Q1 to Q3 is 50%. Quartile suggests that the average of the games played is 71.5. No, remember, quartiles are a measure of like looking at the distribution, not the measure of center. Well, the median's measure of center, but it's all based on the median, not the mean, right? So it's not about the average, it's about the mean. Okay, so we like A. interquartile range. Interquartile range is the distance from Q3 to Q1. To me, that looks like 12.5. 66 to 78 is 12. Another 0.5. Okay, interpret the IQR. When we talked about that, the number of games played in the middle 50% span roughly 12.5 games. Right? The IQR is telling us where 50% of the data lie. D. Five-number summary. Five-number summary. Now those are all. That's max. That's min, Q1, Q2, Q3, max. So we need to find the min. What is the min? I think you are correct. Let's see a lower one on that. And this was 65.5, if I remember. Oh, we got it all over here, right? Median is 71.5, then 78. And the max, 81. Very good. Interpret. The first quarter has the greatest variation. The middle 50% has the next largest variation. And the last quarter has the least variation. What do you think about that? So how much variation do we have here? Almost 30, right? There's almost 30 variation there. This has, what we said, what was IQR? 12.5? Yep. And then this is 13. So the last quarter has the least variation. I think that's wrong because it's 13 is greater than the IQR. See that?
81 minus 78 is 3.
Oh, right. Good point. So that's good. I'm not very good at math sometimes. Okay. So is A? Do we like A? We like A. There aren't as many seasons in the fourth quarter as there are in the first quarter. Why is that false? There aren't as many seasons in the fourth quarter as in the first quarter. Why is that false? They're all the same number, right? So they're all 25%. The first quarter has more seasons recorded. The last quarter has the least amount of, okay, it's the same thing. The middle 50% has the greatest variation in the data set. No, we found the first quarter has the greatest variation. So we like A, despite your teacher. Okay, and 2 parts remaining. Potential outliers. How do we determine potential outliers? We determine those by the upper and lower limits, right? So the upper and lower limits give us a range for non-outliers. Non-outliers, anything outside of those are potential outliers. So does this calculate that for you? I don't think so. So what do we need? We need the first quartile minus 1.5 times the IQR. Did I remember that correctly? And that gives us the limit for potential outliers. Let's write that down. Okay, so 65.5 minus 1.5 IQR is 12.5. Anybody got it? What is that? 18.25. So 65.5 minus 18.25. 47.25. Is that right? 46.75.
12.5 times 1.5 is 18.75.
75. Okay, that was my number. So 46 point what?
46.75.
Okay, so that's our lower limit. And our upper limit would be 65.5 plus. Oh yeah, I just rewrote Q1 again. Q3. 78. Okay. All right, so now we can start with the max and the min. The max is 81. 81 potential outlier or not? No. 81 is within the upper limit, not a potential outlier. So therefore, there's no potential outliers on the high side, because if the max isn't a potential outlier, nothing less than that would be. Okay, what about potential lower limit or outliers that are too small? Our min is 38. Okay, that's certainly an outlier. So, and we'd better look through the rest of the data just to make sure there's not another one. So, after 38, what's the next largest data value? What'd you say? 45 is the next one up. Okay, and what do we think about that? Also an outlier, right? So good thing we checked. So there's actually two potential outliers on the low side. Two potential outliers on the low side, the 45 and the 38. Potential outliers are, type an integer, use a comma to separate the answers. 38 minus 45. Okay. And then the dot plot, the box plot. And so look at our possibilities here. There we go. Let's zoom in a little bit. So do we remember? So it was, what was the next data value up from 45? No, wrong way. The next data value up from 45 is 60 something? Is there any in the 50s? Is it 64? Is that the next biggest? So that's going to be the end of the lower whisker. And then the upper whisker will be the max, because that fell within this. So it's going to, the whiskers go from 64 to 81. Our box is at the Q1 and Q3 profile quartiles. So it looks to me like here's our 38, here's our 45, there's our 64, there's our 81. To me, it looks like C. Agree? So the box plot will always reflect data values. Everything in the box plot is all about data values. That's a data value, that's a data value, and to the whisker is a data value. So those might be those quartiles could be medians, could be little averages of 2, we know. And then the top of the last whisker is data value. See? Okay. Questions on that stuff? Are we good? All right, so let's press on. Okay. Descriptive measures for populations, uses of samples. So remember what we said about descriptive statistics versus inferential statistics. We talked about that on the first day. Anybody remember what descriptive statistics were versus inferential statistics. Tell me, what's your name right here? Tell me your name. Yeah.
Caitlin.
Was it? Caitlin, do you remember the difference between descriptive statistics and inferential statistics?
No.
Okay. Anybody else? Yeah? What do you mean actual numbers? So inferential statistics are actual numbers too, but what do you mean by that?
Inferential ones, like you're like trying to figure something out about a bigger population.
Okay,
Sample size.
right. But descriptive statistics are, in contrast to that. Yeah, so it's it's any values that are just describing a set of data, whether it's a population or a sample. It'll be descriptive if it's talking about just looking at a distribution or calculating an average, or these things are descriptive. But then when we take sample data, sample statistics, and use it to infer about the population, that's population statistics. So let's talk about difference between population and sample stuff. So for variable x, the mean of all possible observations for entire population is called the population mean, or the mean of x, of the variable x. It is denoted mu x or just mu. So when you're talking about the population mean, down here, they use mu, okay? And then the size of the population, capital N. All right? So you calculate that just the way you did. So what does this symbol mean again? Sum up, and what are we summing up? All the data values, all the values of the variable. So each item of the population has a value of the variable x, and so this means go through each one and sum all those up, and then divide by. So this little formula should feel very, very comfortable, in line with what you understand about how to calculate a mean, right? You add up all your test scores, divide by the number of test scores. That's exactly what this is saying. Add up all whatever the data values are, divide by the number of values in the population. Okay. So when we're talking about, say, the population of all U.S. girl teenagers, is this how we're going to calculate the population mean? We're talking about all girl teenagers in the U.S. Is that what we're going to use? No, because we can't possibly find out, like, maybe it's their heights. We can't possibly find out the height of every U.S. girl teenager. Okay? So, let's go back. So for the sample, we've been using these symbols because everything we've been done has been like in the context of looking at a sample. So the size of the sample is little n, and the mean of a sample is x bar. So those are the symbols we're used to. So everything we've done so far has been in the context of we've got a sample, and we're running these numbers on the sample. Caitlin, put it away, please. Okay. So we want to talk about a population standard deviation versus a sample standard deviation. Okay, remember what we said in essence, what is a standard deviation? Standard deviation, look at it, we're summing up a bunch of things and dividing by what? The number of things. So in essence, what is a standard deviation? What is that doing? It's summing up a bunch of things and dividing by the number of things. So what is that? Average. Okay, so it's an average, right? So standard deviation is a type of average. What is it averaging? Remember what we said? What is it averaging? So if you look at this, x, each data value minus the mean. So it's averaging the mean. It's averaging the standard deviation. No, we're finding this. It's creating the standard deviation. Right. Distance from the mean. For every data value, it's essentially, this is the how far it is from the mean, right? And that's what we're talking about, variability. How far are the data values from the mean, and then we're kind of doing an average of that. Now, we square that distance, and we take the square root at the end. So, but in essence, we're really looking at the distance from the mean and getting an average of that, right? So if the average distance from the mean is greater, then the data is more spread out. The average distance from the mean is lower, then it's more together. And so that's how we get standard deviation. Okay, so I hope you're just not blindly copying all this down, because what I was just talking about really isn't what's written on this page. So always tune into what I'm saying, okay, and just make your notes focus about what I'm saying. All right. So this is the population standard deviation. And then you notice a sample standard deviation, they do something different. They divide by n minus 1 instead of n. Okay, so what is this about? So we're gonna investigate that in a second. But here's the deal with this. Population standard deviation is called unadjusted. So it is the true standard deviation for whatever n number of things you do. So it's the true standard deviation for the n things. It's truly this average distance from the mean, or average distance squared from the mean, square root, okay? The reason there's the adjustment for the little s is in order to predict the population standard deviation, okay? So this one is adjusted to infer about the population. We talk about inferential statistics. This is an inferential statistic. This adjustment is what's helping to predict the population standard deviation. So this is the adjusted to estimate this one, the population standard deviation. So you can think of this is like the descriptive statistic. If you have the data values for all n of your things, you can get the true standard deviation. If you just have a sample and you have a large population and you want to estimate the standard deviation, use this a little n minus 1 that adjusts and then is trying to estimate the population standard deviation, or it's trying to estimate this one for the whole population. Okay, does that make sense? So, if you want the true standard deviation of a sample, the true standard deviation, are you going to use the first one or the second one? You use the first one. Consider the sample now your little population. There's nothing outside of it. If you want the true standard deviation of just that little sample, you're going to use this. But if you use this on the sample, now it's like you're predicting what the population standard deviation is. Okay? Someone had a question?
Yeah, I had a question.
Yeah.
So what you say with the first one, I'm just wondering, with population standard deviation, is that like saying the entire population, not just a sample of it? So as
Right.
if we could somehow measure like all the people in the US, for example.
It's only possible if you have a small population and you have all the data for that. Right. If you have, so by population, some populations are really large and we can only do inferential statistics. Other populations are small enough that we have all the data. like we could say that the people in this classroom are a population. And we could find the true standard deviation of whatever variable we're looking at, and we would use that. But if we want to use this class to infer about all STP 226 classes on campus, we'd be a sample, and then their standard deviation, we would use this one. Other questions about that? Okay. All right, so this is what we're talking about. So you have a population data. It has some standard deviations. So diameters of all bolts produced by the manufacturer. Okay, you're not going to measure every bolt that comes out of their factory, right? You're not going to do that. What do? So they go in there and they take a sample of 100 bolts or something, and they get their diameters. And if they run S will adjust and try to infer what this number is, the actual standard deviation for the population. Okay, questions on that? So then our parameters are descriptive measures for population, and statistics are descriptive measures for a sample. And then estimator statistics would be like S. So S is an estimator statistic. It comes from the sample, but it's estimating about the population. All right, so let's see this in action. I've got a data set here. The data set is, this data set here in the first column is all the quiz 1 scores from you guys and from my last time I taught this course. So there are 44 people in both classes, and these are the quiz 1 scores. That's the data. Okay. So then what I did is I took 3 samples, random samples from the data of size 20. Okay, so went through the data and found 20 random values and did it again and did it again. Okay. So we want to look at these numbers, the population standard deviation versus the sample standard deviation, and see what's happening with that adjustment, right? With that adjustment. So if I come here to, if I can look at the data, so let's look at our actual data first. So when I do the actual data, do I want the standard deviation? So here I can come over here, I can clear these out. So I'll do the mean. Do I want the standard deviation, or do I want the unadjusted standard deviation if I'm talking about the data set? Yeah, because if I do adjusted, then it's like trying to predict something from a larger population, but there is none, right? This is our population of test scores, so it makes sense to look at the unadjusted standard deviation. And I'll do the mean. Okay, compute. So I got, for the population, I got a mean of 17.3 on the quiz, standard deviation of 2.38, essentially. 2.38, 2.377. Okay? So now let's start with these 3 samples. And for these 3 samples, would it make sense to look at unadjusted? So summary stats, columns. Do I want to, and I'm going to do those 3 data sets now, or the samples of size 20. I'll do the mean. Does it make sense to do the standard deviation or unadjusted standard deviation? Does the unadjusted standard deviation have a meaning for these samples? Everyone think no? So the standard deviation is for predicting for predicting this, but the unadjusted standard deviation is still valid for a sample. It will just give the true standard deviation of that. So if you're just looking at the sample by itself, isolated from the population, then the unadjusted is okay. And for our purposes, we do want to look at it to see what the adjustment is doing, okay? What the adjustment is doing. So I'm going to show them both. So I'm going to do standard deviation. I lost it here. So try again here. Standard deviation, mean. Okay, so here we go. So notice, here is our standard deviations from the unadjusted, 2.35, 2.33, and 1.98. What's true about all those standard deviations compared to the population standard deviation? You see? They're all too what? The first two are close, but all of them are low, right? They're all too low. If you divide by n minus 1 instead of n, you're going to get a bigger number or a smaller number? You divide by a smaller number, you're going to get a bigger number. So that adjustment is actually predicting, what is it predicting, Mackenzie? What is the adjustment going to predict? Okay, it's going to predict more variability in the data set. Okay, so because it's dividing by n minus 1, it's going to make it a little bigger. So let's see, unadjusted is 2.35. The standard, the S standard deviation, the predictor, look bigger, a little bit bigger, a little bit bigger. Okay, why? Because when you pull just a sample, you don't quite get the full amount of variability that you would get in the population. The chances are most of your what you pick is going to be toward the middle of the data, and it's less likely to get the ones that are outside because they're less likely. So that's why that adjustment, by doing n minus 1, it adjusts for that probably the population has a little more variability than the sample does. And so then, look, those numbers all a little bit higher now. Do you see that those are better? Those are a better predictor because they're a little bit higher of that than these were. So remember, this is our S, this is our S, this is our actual sigma. So remember, so these were all too low. Divide by n minus 1 instead, and it kicks it up a little bit, and then that's the predictor of the actual standard deviation of the population. Does it make sense? Good stuff.
So we didn't use the adjusted one for either of these, but we theoretically.
No, adjusted. This is adjusted. Standard S is adjusted.
Oh.
This is the one that divides by n minus 1 instead. S is the adjusted standard deviation predicting that one. This is the one that I just wanted to show you what happens. So normally you wouldn't calculate this one like you guys wanted to do this, and that was right intuition. It still has meaning on its own, it's still valid, but normally you're gonna get a sample standard deviation to predict the population standard deviation. So remember that the S is the adjusted one. And why is it adjusted? Because you typically see more variation in a population than you will get from a sample, because a sample will more likely be the ones that are more common around the center of the data. Okay, questions? All right. So let's go on to the next thing. Okay, z-scores. Okay, z is called a standardized version of x, or standardized variable corresponding to the variable x. Okay, so z-score. For an observed value of variable x, the corresponding value of the standardized variable z is called the z-score of the observation. The term standard score is often used instead of z-score. So standard score or z-score is standardized version of x. And so we're going to see what that does. So it gives us a value that we can then compare from in totally different contexts. So we can compare z-scores from different populations, different samples, totally different contexts. It has a way of comparing those, okay? We're standardizing it. So it's a common scale. The z-scale is a common scale that works for any population, any sample. Okay, so let's see that here. So we have frog thumb length. 2 museum researchers collected information on the lengths of the widths of different body parts of male and female frogs. I won't even try to say that. Thumb length for female frogs has a mean of 6.71 millimeters, standard deviation of 0.61. So is this this is the mean? Is it going to be mu or x bar? So this stuff right here, is it population or sample data, sample statistics? Would have to be sample, right? There's no way we could get every frog of the species and measure their thumb length, okay? So this would have to be from some sample. Millimeters. Okay, so the standardized version of x we just said was z, right? So z equals x minus, what did it have? Let's see. Oh, so it's talking about population. So that is population data. Okay, so this, they're talking about in the population, right? Because that's population mean and population standard deviation. So they're talking about this being mu. And this being sigma. So they've already run the numbers. They've taken lots of samples. They've crunched all the numbers, and they're saying this is our population data. This is our population data. Okay. So the standardized version of x is what I just told you. It is z x minus mu over sigma. Okay, so they want us to compute z-scores for 5.2 and 8.1, but those are just going to be numbers, and they won't really make sense. So what we want to do first is we want to make, let's set up for the population, let's set up our scale and our ranges, and I want you to do that, right? I want you to do that. So we want to get a feel for what the data is like by setting up the ranges of 1 standard deviation above and below the mean, the range or the interval of 2 standard deviations above and below, and 3 above and below. So I want you to set that up. So where's 6.71? So maybe make a number line here, 2, 3, 4, 5, 6, 7, 8, 9. Make sure here we got enough. 10. Okay, so I want you to make the ranges. Make the ranges about, so using the population mean, the population standard deviation, make our ranges so we get a feel for what this, what female frog thumb lengths are like. Okay, so this one's for your notes. This is not for the sheet. Sorry, this is for your notes. The sheet's for the next thing we do. We're going to do this together. Right back. Okay, did you get the range for 1 above and below? So the lower bound of that is, we're going from 1 standard deviation below to 1 above. What are the numbers? What we were supposed to be doing. You're making the ranges from one standard deviation, 2 standard, and those are numbers involved in that, right? So now I'm talking about 1 standard deviation above and below. What are the numbers? 6.0 something. So right about here. And 7.38. And what's significant about that range? What is significant about that range? What? That's right. And when we're talking about a population, it's not about, it's going to be 68%, okay? So if it's, If it's a sample, then we can just say if it's a small sample especially, we can only say it's going to be about. There's no guarantee. But if it's a population, then it's going to be, and it's a large population, it's going to be right at about 68%. If it's a normal distribution, okay, so we'll talk about that later in the course. But for a normal distribution, this will be 68% of the data, okay? Then what is our next from 2 standard deviations below to 2 standard deviations above? What are those numbers? 5.37 to 8.0 something. Okay? So I need this to be further this way. Okay, so there's that range. And what's significant about that range? All right, so this is really telling us about this population in terms of thumb length. This very interesting and intriguing thing. Thumb length of these female frogs. 95% of female frogs of this species have a thumb length between, what'd you say? 5.37, 5.38, and 8.05. Millimeters, okay? And then the last range? 4.7? And 8 point. Significance of that range? Virtually all the data, except maybe 1%, okay? Almost all the data falls in that range. Okay, so then let's look at for a thumb length of 5.2 millimeters. 5.2 millimeters. So where does that fall on the scale here? So the first data point is right here. And so what can you say about this frog's thumb length? This frog's thumb length. What can you say about 5.2 millimeters? It's outside of the 95% range, right? So it's particularly small, right? Particularly small. And then 8.1. Also not in the 95 percentile, right? So not in the 95%. So this is particularly large thumb frog. Okay, so now let's get the adjusted scores and see what these mean. So if we use z equals 5.2 minus 6.71 all over 0.67, what do you get? Negative what? No, that's not right. Something's wrong. It should be like negative 2.1 or something. Did you do this whole thing in parentheses? Yeah. What is it? There we go. Negative 2.2. Okay, so what could that mean? Negative 2.2. Can you look at what we did? Look at that 5.2 where it lies in the scheme of things. What does that number mean? Can you see it? Can anybody recognize what that number is telling us? Negative 2.2. Negative 2.2 what? What? How? Negative 2.2 what below the mean? Standard deviations. Do you see it? It's how many standard deviations below the mean it is. Because this was 1 standard deviation below the mean here. 2 standard deviations below the mean was 5.38. And we know that this was a little bit less than that. So look, a little bit less than that, negative 2.2. So z-scores are numbers of what? are standard deviations above, okay, or below negative, like we got in that example, the mean. That's why they're standardized, because we know how the standard deviation works. We know that it's always 68%, 95%, 99%. So by finding a z-score, you're finding a number of standard deviations away from the mean. All right, so what would you predict? Don't do the math yet. What would you predict for the z-score of 8.1? What would you predict for the z-score of 8.1? What do you think it's going to be? About what? Less, more, or greater than 2? So it's 8.1 millimeters versus what is exactly 2 above? 8.05. So this z is going to be a little bit, yeah, a little bit greater than 2, because it's a little bit greater than 2 standard deviations above the mean. Okay, find it. So find the z-score for this data value 8.1. .07 sounds right. Okay, so if I can make a new scale now. So at the mean, what is the z-score? So this red one is going to be my z-scores. At the mean, what's the z-score? 0. You're no distance away from the mean. No, you're at the mean. So that's going to be 0. This would be 1 right here. Or -1, sorry. -1. And this would be 1. I'm lining everything up here. This is 2. And this is -2. And then this is 3. And -3. So our first data value of 5.2 millimeters fell right here at minus 2.2 standard deviations from the mean, or 2.2 below. Right? So that's lines right up. See that? And then the 8.1 was just about right at 2, just a little bit bigger than 2 standard deviations above the mean. So it's standardizing because no matter what the scale is up here, in the thousands, if you're talking about a variable where the numbers are in the thousands, or a variable where the numbers in the the range of 0.05. So it doesn't matter the magnitude of your numbers. It standardizes it to standard deviations. Standardizes it to standard deviations so that we can compare. So we know what that is. So we know, okay, 5.2 millimeters. Well, that's -2.2. The z-score is -2.2. So we know it's like, oh, it's outside of the 95% range. This is a particularly low data value. It's not an outlier, but it's particularly lower than the mean. And then 2.0. Again, this is relatively large thumb length. Okay. But we could have another population with the variable values in the thousands, and it would standardize to this exact same scale, -3 to 3, with 0 at the mean, right? With 0 at the mean. Okay, does it make sense? So know that when you're finding z-scores, you're counting, it's a distance of standard deviations from the mean. If it's negative, it's that many below. If it's positive, it's that many above. Okay, anybody have a question on that? Okay, so let's go back to our population here for your sheets. So we'll use this data right here. So this is true sigma, right? This is a true sigma, and this is a true mu for all the quiz scores from both classes, right? So I want you to find the z-scores. So make a scale of the ranges. So 1. Make the intervals. On a nice number line like we've been doing, okay? And then predict z-scores. Don't calculate them. Based on your intervals, predict the z-scores for a 20, a 16, and half right, 10. No, let's do 12. No, let's do, 10. And then find the z-scores for 20, 16, a score of 20, 16, and 10. So you're making the intervals for our population of quiz 1 scores from my 2 classes. Predict the z-scores. Now, based on your intervals, look at the intervals. Don't do any calculations yet. Try to predict what a z-score for 20 would be, what a z-score for 16 would be, and what a z-score for 10 would be. And then find them and see how you did predicting. Okay? And that's for your blue sheet. Whenever I have you do something on the sheet, you can always put it in your notes as well. You're welcome to do that. Okay? And truly, do your best to predict. And if you're not sure, then talk about it before finding those numbers. So we really want to try to understand what those numbers are. And this idea of estimating or predicting is a really good way to see if you understand what's going on. So truly, be honest and serious about number 2 and work together if you need to before doing number 3. What's that?
Can I do this as homework? I need to go to my next class.
Yeah, you can just write it down and email it in to me. You can even email it and just do it later today. Not the median. What do you want the median for? The mean, the standard deviation, make the intervals. The median would be using for the box plot. Yeah, it's always, when we make the intervals with a standard deviation, it's always centered on the mean. Always the mean. You can just use so you can use 2.38. I don't know what you decided to round at, but I think it's appropriate to do 2.38. and 17.3. That would be an appropriate rounding in this case. 17.3 for the mean, 2.38.